Hey folks, thanks for joining me today on Cyber Llama Talks. Today we're going to talk about process emulator and how exactly the CPU emulator has evolved into being a process emulator and how it allowed antivirus products to detect polymorphic and encrypted malware better. Last time we talked about CPU emulator and how it was used to emulate a binary executable from Windows instruction by instruction to unroll encryption or polymorphic layer of the malware, so then signature can be applied on a original binary. So just to remind you what we discussed last time, right, is emulator has a vCPU stack and virtual memory management. That's the main components. vCPU is responsible to keeping all the information about current state of virtual CPU, which is emulated. Stack is the virtual stack, and then VMM is responsible of mapping the original file into memory space of emulator, and also translation of the original virtual addresses, the source virtual addresses of the malicious file into the virtual addresses inside the emulator. So when instruction tries to read source virtual address, it actually gets translated to target virtual address, and the memory is read inside emulator process. And so we have these structures, data structures, and what happened during the emulation is each instruction starting from an entry point gets fetched, that's disassembled, right? So we fetch the bytes, we disassemble the bytes into instruction. Instruction gets to the table, there is a table lookup, and depending on the type of instruction, this certain interpretation function is going to be executed to actually interpret how this instruction affects virtual CPU, virtual stack, virtual memory, and then EIP gets updated, and everything happens all over again, right? It fetches next instruction, disassembles, lookup, interpret, and so on. And we already also discussed all the weaknesses of such approach if it's just CPU emulation in our previous videos, so you can always look it up and see. I'm not going to go over it again. Instead, I will show you what has changed between CPU emulator to a process emulator. So from the name, you can already kind of assume that we're going to talk about not just the CPU emulation, right, these three structures, but also a process emulation. And what does it mean specifically in the context of malware? Of course, we don't really need to emulate the whole process, the entirety of process inside the operating system. I mean, we can, but that would be extremely complicated and would require a lot of resources. That being said, for polymorphic malware or unpack polymorphic malware, we don't necessarily need everything. We just need to make sure we support most of the use cases malware uses. So what are those use cases? Of course, and we discussed it last time, that PEB, the process environment block, TEB, thread environment block, and process environment variables are crucial if we really want to emulate the process, the malware, because assembly code can easily access it through ES and also in 64-bit GS segment. And if malware runs on the real system, it will get access to PEB and TEB through those registers. But of course, if emulator has to support it as well. So that's the first essential thing. It's especially essential because a lot of polymorphic malware, and most of polymorphic malware actually, had to be pretty much based on a position-independent code, meaning that code has to be able to run no matter where it's actually loaded in the memory, meaning it cannot actually rely on the import table. First of all, relying on the import table, it means exposing your intent, right? And no one wants to expose the intent of malware right in the import table. And the second, it means, again, you're relying on the PE structure, and if by some reason you need to run a different memory, and especially if you're multi-layer or packer, right, you need to be able to run from any position in the memory, you cannot rely on the import table. So the polymorphic packer had to get all the API addresses dynamically, and usually what they would do, they would go to the PEB, enumerate all the libraries loaded into process, find needed libraries such as kernel32 or ntdll, and then from there would find the exported function, compare it with the name, and then find the address of the exported function so it corresponds to the function it needs. It means if you don't emulate PEB and TEB, pretty much everything fails, right? You cannot emulate really a shellcode, or you cannot emulate polymorphic decryptor. So that's the first thing. Another very important addition was to extend how exactly call and job instructions are handled. Of course, we can interpret call or jump instruction just a regular assembly instruction. The problem is if that's the import call, when the binary is not loaded, it would actually point to the address which points to a string inside the import table. And that would be just a string to the name of the API function that requires to operate. So if we just blindly emulate jump or call instructions, most likely it would just crash. The process emulator has to be aware about import, which binary would have. And so what happens here, so it means every time it sees the call or jump, it needs to have a special treatment and actually analyze not just what instruction would do, it would need to analyze the address the call or jump points to. By analyzing the address, it can recognize that address actually points to the import table, and from import table understand what function it's trying to call, and after that it can actually emulate the API. And after that emulated, we just return back. Emulating API is not a simple business. It means the emulator would need to know ABI, the application binary interface, how exactly parameters get into the function. For example, in 32-bit, that would be through the stack in most of the cases, and how they actually return. There's also a complexity of what function calling convention is. For example, it can be std call, it can be cdecl, or a bunch of other conventions, and depending on the convention, the parameters to the function will be passed in different registers or different order and stack. So it's not like all the APIs are going to be emulated the same way. It means emulator would need to contain the list of APIs and also interpretation function or emulation function for every API. And those emulation function would need to know the parameters, would need to know what to return, because depending on the function, it might fully emulated or partially emulated, or just have a very simple stub which doesn't do anything and just returns 0 in some cases. And it also have to know what return value are. Is it just a EAX, or is it just a structure the function needs to allocate, or 0, or fill with certain data in case if the API expects return data being returned through the reference, for example, or the pointer. So each API has to be emulated, and then the emulation goes back to the original image, and the whole cycle goes again. That's a second edition. We already have tab, that would be first edition, that would be our second edition. So now we know how to emulate tab, we also know how to emulate APIs. So what else? Another special instruction would be a SYSCALL, or to be more precise, it's actually SYSENTER, as well as interrupt instruction for Windows 2000. So the idea would be very similar, right? It would need to know the parameters of SYSCALL, SYSENTER, need to know how to interpret those parameters and what to do with them. But the idea would be simple, you're just extending the emulation of API also with the SYSCALL and SYSENTER. It's very similar. It's a different instruction, but interpretation-wise, the SYSCALL is just another API call through special instructions, so there is nothing specifically complicated about that. So I simplified the diagram a little bit just to give us a bit more space, right? We talk about this emulation loop, and we say that process emulator has to add call, jump, SYSCALL, and into each special emulation cases to support interaction with the operating system, but that's not all, right? Some of the interaction with the operating system might be a bit more complicated than just one API call emulation. For example, such API calls like create file and then write and read actually requires state. If malware just calls a create file once and you emulate it and just return a successful value, that might work. However, if malware then writes to the file and then reads from the file and tries to see if actually what malware is reading to the file is equal to what it's read from the file, then you're in trouble as an emulator. Because if you actually don't have a context and you didn't store the context of the file, content of the file on somewhere, you're going to be in trouble. Of course, it can be held in the memory, the whole file. You know, it gets cumbersome if malware writes hundreds of the files and so on. So one technique how to handle it would be a pass-through. In this technique, what emulator can do, it can actually call create file, write file, and read file API on the system, but from the context of emulator. And instead of calling it with the original path to the file, it can call it with virtualized path. Meaning, if malware wants to create a file, C Windows a.exe, the virtualized file would be somewhere in antivirus directory, whatever antivirus wants. It can just, you see, remove the semicolons and just combine the path, right? So it means the AVDIR in this case acts like a root of the file system, and everything written on the file system inside the malware, it's actually written inside this directory. Of course, Emulator has to be careful and make sure it doesn't contain any vulnerabilities and exploits, so malware can actually access the real host's file system. But if implemented correctly, then Emulator can actually maintain the state of all the files created on the disk. With the network is a bit more complicated. You definitely don't want a malware to connect to network from either the endpoint you're protecting or from your antivirus lab. It means connect and all other internet, the web-related API functions. I guess they could be implemented in multiple ways. For very well-known domains, it could just always return the same traffic or the same list of virtualized IP addresses or whatever. It kind of can try to emulate the web, right? So if malware, for example, connects to google.com to check if it runs online, it can return whatever emulated page. The problem here is that process emulator cannot always know which domain actually exists. And without querying the domain, you would not know if it's available, if it's online, and it should be available. And you probably heard this story from WannaCry when the wait was completely disabled by registering domain. So I believe that in WannaCry what they actually tried to achieve, they didn't try to bypass any sandboxes or anything like that, that most likely they just tried to bypass process emulator, because in process emulator you really cannot have a real context of the network, so most likely most antivirus companies would just always return something. And so what WannaCry did is, the first thing it did, it tries to connect to non-existing domain. And if you connect to non-existing domain in the process emulator, it exists, right? And so, well, of course, the malware author didn't think about, well, if someone actually registered that non-existing domain, then whole malware dies. Didn't think about that, but that's probably what attack was against. And such type of emulation already existed even much earlier than WannaCry, somewhere 2005, 2010, depending on antivirus company and sophistication of the product, something like that would exist there as well. Thanks for listening. I hope now you know better how process emulator works and how it helps to detect polymorphic and packed malware. In the next videos, we're actually going to talk about how process emulator allow to build new technologies to detect malware, and specifically we'll focus on behavioral analysis and memory analysis. Stay tuned, subscribe, and hopefully I'm going to see you in the next episode.